Welcome to this third and final lecture in the NESCAP machine learning course. What we're going to do in this lecture is bring together the material from the two previous lectures. So what we're going to be looking at is text-based prediction and classification. So it's a mix of the machine learning, extending a little bit the techniques that we looked at in the first lecture, and then combining it with our ability to process text and get it into numerical form from the second lecture. Now, in terms of what I'd like you to take away from the session, the key point is really about a different kind of machine learning tool that we're going to use in this session. It's called an artificial neural network. And as we're going to see, they're very powerful prediction tools. The philosophy, it's very different from what we would see in a kind of classical econometrics regression style problem. The emphasis is really about learning. So when we talk about deep learning, which is a term that you've probably come across in different contexts, we're really talking about applications of particular types of artificial neural networks. So the idea is that we get a model to predict and to learn from the errors that it makes when it predicts. Okay, so basically we make a prediction, we adjust, we make another prediction, we adjust, we make another prediction, we adjust, and so on and so forth. And so that's the kind of learning process that we're talking about. So second point, artificial neural networks are technically relatively complicated. If you want to understand the algorithms and everything that go into making these work, there's a bunch of reading that you can do about it, but it does start to get fairly complex. Now, having said that, the intuition, I think, is actually pretty easy to grasp. And for our purposes, given that this is a crash course and that the emphasis is on learning by doing, all we really need is an intuitive understanding. So once we get the basics in place, it's actually pretty straightforward to start using them quickly. Workflow is going to be very familiar to you from lecture one. There are some modifications, of course, for the different type of model, but the general workflow is the same sort of machine learning workflow that we've looked at. Now, the reason why I'm introducing artificial neural networks is that they work very well with text as an input. Okay, so other techniques, regression-based techniques, tend not to do so well. Artificial neural networks, for various reasons, do quite well with text as an input. So it's perfect for our purposes. In terms of implementation in R, as usual, there's a package for that. In this case, it's primarily a package called Keras. It offers a very powerful way of accessing some high-level code on artificial neural networks, but it makes it very easy to do. So we're going to be focusing on how exactly to make it work here. Then in terms of economics, well, economics is not using neural networks very much yet. So I think there's huge perspective to have an impact on the literature by using some of these models. Okay, so what I'm going to step you through in the lecture is really 5 parts. The first 3 are going through the material to sort of introduce the intuition, some of the steps that we're going to go through in the code. And then the last 2, we're going to do, in this case, 2 demonstrations in R. The first one is just showing you how a neural network operates using the LPI example from the first lecture. So that's a simple sort of quantitative prediction exercise. Then we're going to do an example of a text-based classification prediction exercise in the second demonstration, where we're going to be classifying some non-tariff measures using an artificial neural network. Okay, so let's give a little bit of motivation for what we're trying to do. As I said, in the 2 lectures so far, we've looked at the 2 main ingredients. We've looked at some basic machine learning tools, and we've looked at some basic text as data tools. So what we want to do in this part of the course is bring those 2 things together and look at how we can use text as data in the context of a machine learning model. So basically, how complicated do we have to be to try and get text as something that we can use to predict a quantitative variable or a classification or some kind of variable that we're interested in. Now, to do that, as I said at the outset, we're going to introduce a new tool called an artificial neural network. These are the sorts of tools, obviously much more advanced versions than the ones that we're going to be looking at, but these are the sorts of tools that power automatic translation, predictive text, and all these sorts of things that we see in our everyday lives. When we start looking at artificial neural networks, the workflow should be quite recognizable from the workflow that we looked at in lecture 1. But the way in which these things work is fundamentally different. The philosophy, I think you'll find recognizable, but the actual way in which they operate is quite different. So I think it's useful to use just a really standard, straightforward prediction problem to try and set up the intuition, and then we can move to text after that. Okay, so where we would ultimately like to get to, and where we are going to get to, is this problem. So on the left-hand side, I've got an extract from some data that you can produce with UNCTAD's TRAINS database. So TRAINS is a global database of non-tariff measures. And what it does, you can see there that I've marked with a blue line the output that we want from our model. And the output is an NTM code. Okay, so NTMs are classified using what's called the MAST classification. This is a classification that the major international organizations have agreed on. It's an alphanumeric code. So the letter identifies the main type of NTM. So is it an export related measure? Is it contingent protection? Is it SPS? Is it TBT, et cetera, et cetera? And then the numbers indicate categories within each of those chapters. Now we're going to be interested in the letters. We're not going to do the full alphanumeric code, but ideally what we'd like to do is take this input that I've marked with a red arrow. As you can see, that is a verbal description that a human coder has put in to summarize a particular measure that they found in some countries' law. In this case, it's Afghanistan. They found this measure, they write down basically what the measure is about, and then they themselves classify it using the MAST classification. So what we'd like to do is to take their text as input and then to produce the classification scheme in blue as the output. Okay, so that's our basic problem that we're trying to solve. Now, one reason why we might want to solve a problem like that is to reduce the amount of human input that has to go into this classification exercise. So the idea is once you've done a certain amount of training to get the relationship between text and classification, maybe you just let the computer go and let the computer do it all on its own. Now, the more advanced way of thinking about this problem is, can we cut out the description, which is our input in this case, and actually just use a full domestic law? Okay, so you could imagine an approach to solving this problem where you have web scraping to pull down the text of domestic laws from each country. Then you have some sort of algorithm that's going to go through the text and identify NTMs and then classify them based on this MAST classification. So that's obviously a much more complicated problem than the one that we're going to look at, but that's ultimately where work in this area is going, to try and automate this kind of coding, which at the moment is done exclusively by human coders. Okay, so hopefully when I describe the problem like that, you can see two stages that we've got to get through. One is to turn this short text description into input data. And then once we've got the input data, we want some sort of model that's going to allow us to turn the input data into the output data. So now hopefully when I've said it that way, you can see, aha, this is exactly what we've been talking about separately in the first two lectures. So this really is kind of bringing together the insights that we've already looked at. Much of the workflow is going to be familiar to you. We're going to pre-process the text. We're going to use cross-validation, all these sorts of points that we've previously looked at. But before we can get very far, we need to introduce a more advanced machine learning tool, which researchers have found works pretty well with text. So that's where we're going next. I want to introduce this idea of an artificial neural network. Now, when we started talking about machine learning, we started with what I called the lasso family. So remember, that was lasso, ridge, and ElasticNet. Now, the reason I started there is not necessarily that they're the best machine learning techniques for every problem. Obviously, they're not. They work well for some, not so well for others. But I think they're a really easy place to get into the literature if you have an econometrics background, because you can set a lasso or a ridge or an ElasticNet up in a way that looks like a standard regression problem. And so then once you sort of know the techniques that we're dealing with, it's really just an adjustment in mindset to say, okay, we're no longer particularly concerned about inference, which is the classical econometrics problem. We're going to focus on prediction, which is really the machine learning problem. Now, artificial neural networks take that philosophy one step further. The emphasis is almost exclusively on prediction. Okay, there's really not much that we can do in terms of inference with artificial neural networks. So when we report the results of a model in the way that we're used to doing in an applied paper, there isn't really anything like a coefficient. There are various types of weights that you can pull out of the model, but it's it's atypical to include anything like a list of coefficients. There's no idea of statistical significance or anything like that. All we're going to report is how well the model does at predicting. Okay, so the focus is almost exclusively, in this case, on prediction accuracy. Now, the math behind these things starts to get a bit more sophisticated. We're not going to go into it at all in terms of the mechanics of the algorithms that power neural networks. If you want to do that, there's a range of standard texts that you can look at. But I think the intuition is relatively accessible. So what we're trying to do in this lecture is to look just at the intuition behind how an artificial neural network works, and then on a practical level, the different choices that we have to make when we're solving a prediction or classification problem with an artificial neural network. Okay, so how do we get from inspiration to implementation? Well, as the name suggests, the implementation comes from a very simple model of how the human brain works. Okay, so in the human brain, you've got a huge and very dense collection of neurons, which are sort of nerve cells in the brain. And they are stimulated in a particular way. That's the inputs, which we're calling X there. They go through a series of operations and then they produce an output. Okay, so they stimulate other neurons or other parts of the body using that output. So that's the basic idea of how our neural network works. And so what we're doing with an artificial neural network is to try and code that. Okay, so a very sort of simple inspiration behind that. And basically what we get is three components. We have an input layer, that is to say we have a group of what we would think of as variables, right-hand side variables in a regression model. These are the inputs that we're using to do the predicting. Then we have a hidden layer. Okay, each of the inputs goes to the hidden layer using a particular weight. And then from the hidden layer to the output layer, the data is mixed up, reweighted, and turned into a composite that is then called the output. Okay, so when we think of the structure, at the entry point, we need one neuron per component. Okay, so the number of data points that we want to act as inputs, we need the same number of neurons to get the input from each of those. The hidden layer can be whatever number we want. Okay, and so that's typically something we have to experiment with in the course of solving a problem. Then the output layer is going to have a number of neurons equal to the number of outputs that we're interested in. Often it's just going to be one, but we're going to look at a context where in fact we have a whole bunch of outputs. Okay, so to get a little more technical about how this works, this is the basic structure on the left-hand side. So we have our inputs again, these X's, we have our weights, the W's, and then we have this exogenous bias factor. Okay, it's called bias, but it's basically, you can think of it as just sort of an additive factor that gets added to each bunch of inputs. And all we're doing then is combining all of these elements using a mix of the bias, the inputs, and the weights. Okay, then once we've made the combination, we've got an activation function that passes that combination to the output. Okay, so the way in which all of this works, you'll notice that there's no regression problem anywhere in this. It doesn't look like ordinary least squares. It's got very little relationship to ordinary least squares. What we're trying to do is to learn by using inputs to produce outputs. Okay, and the basic technique is that by getting the model to do this over and over again, it can refine these W's, that is to say the weight that's given to each input, in such a way that predictions get better and better. Okay, so it's very much a recursive technique. So we're having a guess of some weights, we're looking at how good the prediction is, and then we're adjusting the weights based on the difference between the predicted value and the observed value. And we're doing that over and over again. So we can then take this linear combination of inputs weighted by the weights and send it to the output in a non-linear way. Okay, so the activation function can be either linear or it can be nonlinear. So it does give us the opportunity to get nonlinearities into the model, okay, which is part of the reason why neural networks tend to do better in many prediction and classification settings relative to traditional techniques, which are largely linear. So then to relate all of this to deep learning that you've surely heard about in different contexts, really all a deep learning model is, it's an artificial neural network with multiple hidden layers. You're simply stacking the hidden layers one on top of the other. It could be a small number, it can be a large number. Now, there's all sorts of variations on that. There are all sorts of different types of neural networks. What we're talking about here is the simplest version, but it hopefully gives you the building blocks for understanding all of the rest. Okay, so learning, as I said, is really getting to the recursive nature of the problem. I try a set of weights and then I learn from the difference between the observation and my guess, my prediction. A common algorithm for doing the learning is called stochastic gradient descent. Basically, what that tries to do is that it takes a loss function, which you define beforehand, and then it tries to minimize that function given as constraints the data that we've got in the input layer and the structure of the model. Okay, and to just sort of demystify the terminology a bit, we talk about gradients because we're talking about the error gradient. Okay, so what we're trying to do is to move down the error gradient and find a minimum. Okay, so to find a point that minimizes the error that we're observing. Now, as I said, the details get a bit complicated. We're not going to get into that, but the basic idea is pretty straightforward. You initialize the neural network with random weights. Then you take the inputs and apply the processing in each layer. You combine inputs and weights, you regularize it all using the activation function, and you pass it to the next layer, if there is one, until a prediction of the output can be made. Then you calculate the prediction error, calculate the gradients of the loss function, and use that information to decide how to adjust each of the weights in the model, and of course there can be lots of them, so as to move down the loss function. Then you repeat that over and over and over, okay, until your prediction hopefully gets better and better. Okay, so, doing this, there are a lot of hyperparameters that go into the model. Okay, so, when we think of a regression problem, we're interested in parameters. That is to say, things the model is estimating. When we talk about hyperparameters, these are basically the structural parameters that are going in to define the model. Okay, they're telling the model how to work. It's describing how the model learns. So, a simple one, how many layers does the model have? Within each layer, how many neurons are there? Is it the same number in each layer or is it different numbers? Are we going to use dropout rules? So that's a way of trying to reduce overfitting, where we say that there's going to be a percentage of each percentage of nodes in each layer that are randomly set to 0. Okay, how many samples will we have in each batch? Okay, a sample is an observation, and a batch is the set of data that goes through the model before updating the weights. Okay, so how do we set up this sort of observation and batch relationship? How many epochs will the model be run over? An epoch is an iteration. Okay, so going through the data set once is one epoch. Are we going to run it 100 times, 500 times, 1,000 times, 10,000 times? Okay, all of that has to be decided. How are we going to assess loss? Which function are we going to use? And then, of course, there's a whole bunch of others that I'm not even going through. Now, when I describe it like that, you hopefully think to yourselves, aha, if there's no magic in setting these, if there's not a formula that I can apply, maybe I just use a grid search. Okay, what I'm interested in is prediction. So maybe I just cycle through all the different combinations of these hyperparameters and I look for the model that has the best prediction performance. And that is, of course, exactly what we would like to do. The difficulty is that because all of this is multiplicative, okay, so if you think of the way that you would do the combinations of this, you're multiplying numbers by each other, you very quickly get up into millions or even tens of millions of models. So you start to make your computer very unhappy at that point, and you've got to be very patient because this can take quite a while to go through. Now, one way that we can try and cut down the amount of time is to use a stochastic approach, so a grid search, but with an element of randomness. So what we essentially do is choose another hyperparameter where we say, conduct a grid search over this parameter space, but only look at, say, 1% of the model. Okay. It may sound like that's going to be a worse approach than looking over every model, but actually you can show, and this has been demonstrated rigorously, that for a given investment of computing power, say that you've got 2 hours of server time in which to do your search, you're actually going to be more efficient using the random search rather than a full grid search. And the reason is with the random search, you can search over a broader space in a given amount of time. So you're more likely to find the best performing models. Typically what we find when we do this sort of grid search is that there's actually a bunch of models that perform pretty similarly. So what we're going to try and do typically is to choose the simplest model among those possibilities. So more complex models are not necessarily better. And overfitting is something that we have to be very careful of with artificial neural networks. It's very, very easy to overfit. Okay. Just missed a slide there. Okay, so a key advantage of neural networks, as I mentioned earlier, is the ability to introduce nonlinearities through the activation function. Now, I've listed here some of the typical activation functions. So remember, an activation function is the way that the one neuron sends its information to the next link in the chain. Okay, whether that's the output layer or whether it's another hidden layer. It can be as simple as a linear function, in which case it's simply the kind of linear transform that we're used to. It can be a rectified linear known as ReLU. This tends to work pretty well in a lot of machine learning applications. It's called a rectified linear because for a value of the function above 0, it simply takes the linear form, but then negatives shift to 0. Okay, so it's just applying a simple adjustment. And this is something that we see a lot in hidden layers in neural networks. We can use a sigmoid. Okay, that's so a logistic function is from the sigmoid family. This is typically what we're going to use for a binary classification problem where we want results to be either a 1 or a 0. We don't want sort of numbers between them. Then we can generalize that to a multinomial version of the same problem. So where we're doing a multinomial classification problem, we're going to typically use a softmax activation function. Now, these are just a few examples of activation functions. There are actually lots of them, but these are the 4 that you're typically going to be using at different points in simple neural network problems. Now, ideally, of course, we'd like to use some sort of cross-validation to see how well the model is doing out of sample. In an ideal world, it might be k-fold cross-validation, but the computing time, at least in the applications I'm familiar with, is generally prohibitive. So we do this split into testing and validation. We'll be doing that at 2 levels. One is that the neural network is going to assess itself using a testing training split. And we're then going to do another level of validation on top of that. Now, you can quickly see that it starts to become quite intensive in data. These really are sort of big data techniques. We're going to be using them in some applications with a relatively small amount of data. And that's something you always have to be quite cautious about. These models typically need a lot of data to really learn well. When we look at how the model does, as I said, overfitting is a real risk with the neural network. R is going to print out some diagnostics for us on the neural network. And the way to very quickly see if we're overfitting the model is to look at whether or not the validation loss and the training loss are roughly the same. Okay, if they're roughly the same, then we're not overfitting, meaning that we're doing about as well with the training data as we're doing with the validation data. If we see that we're doing much better with the training data than we are with the validation data, we're probably overfitting. Okay, so we're getting a model that does really, really well with the data set it was trained on and not so well when you introduce new data to it. So again, that's something to be very careful of as we go through. Now, the basic workflow should be quite recognizable to you. There are a couple of tricks. So the data pre-processing requires a bit of work. Now, the reason is, again, that we're using libraries that are fantastic. They're very powerful, but they're not as user-friendly as some of the regression libraries that you're more familiar with in R. So we typically need to get the data into the form of matrices. Okay, so Keras and the other libraries that we're looking at typically don't like receiving data frames as inputs or outputs, so they want to see matrices. So that's fine. We need to normalize the data. So this was something Lasso and ElasticNet and all these things, they do it automatically. When I say normalize, we're typically going to mean transforming each of the variables to be on the same scale. And that scale is usually going to be a mean zero unit standard deviation variable. Okay, so for all the variables in the data set, we're going to subtract their mean and divide through by their standard deviation to put them on that scale. It's pretty easy to do in R, but don't forget it, because neural networks can just break down completely when you have data on radically different scales. Then it starts to get familiar. We do this testing, training, split. We set up the model. We run the model. We look at how well it predicts. We repeat the process over a set of plausible hyperparameters. So this is the grid search that we're talking about. We choose the model with the best predictive ability. Then we produce out of sample predictions and check the accuracy of our preferred model. So that's a really quick introduction to neural networks. How do we get text into the problem? So how can we use text to try and power a neural network? Well, we're already most of the way there. We've seen in the previous lecture that with the right pre-processing, it's actually pretty easy to turn text into numerical data that we can hopefully work with in a reasonably similar way. We're going to go all the way with that application in the context of a neural network. We're going to turn the text into numbers, and we're going to use that as our input. We have all the tools already to do that. And so we'll just step through them again here to remember exactly how it works. Now, the first step, of course, is to pre-process the text. It's not going to help our model if we've got stop words in there, for example. So we need to get rid of those. We need to tokenize the data. That is to say, get this nice vector where we have each word and word counts and all that sort of thing. And we're going to lemmatize, so to try and use just the meaningful part of the word as opposed to the grammatical function. Okay, then once we've got that, we go through and calculate our word counts. That is to say that that's the number of times that each word appears in a given piece of text, so a document, for example. Now, normally in a long text document or a large database, there could be tens of thousands of words. That's going to be hard to work with, both because a lot of those words are not particularly meaningful, and also because it's just going to make the model run very slowly. So usually we're going to cut off the number of words that we consider to be some subset based on the most frequently occurring words. Then the key step is to take this vector of word counts and transform it into a document term matrix. Now, you remember a document term matrix from when we looked at the latent Dirichlet allocation. We're going to look at it in a little bit more detail here, just to get a sense of what exactly it looks like. So here's one here that I've prepared using the UNCTAD data. So this is how we want the data to be organized. Measure there is an individual document. So you can see there's just an index there, measure 1, measure 2, measure 3, etc. So we want one row per text fragment. Okay, and in this case, each fragment is a description of the NTM. Then we want one column per word. So here you can see the first word is livestock, then there's the word export, then there's the word ban. And you can see that each of those first 3 words appears once in the first measure. Then we see export and ban appearing once each in the second measure, etc., etc. So each cell indicates the number of times each word appears in the text fragment contained in each row. Okay, now we're doing it with counts here. You could also do it with TF-IDF, for example. That's sometimes going to work a bit better. You can do it with frequencies. So you can experiment and see which of these gives you the best performance. Now, once we've got the data set up like that, that should start to look pretty intuitive, because that really looks like, you know, in the first column, we've got an index. In the second column, we've got code, which is our output variable, our classification code. And then we've got all of our right-hand side variables coded as numbers, as usual, following that. So it should start to hopefully look like the sort of data that we can work with. So that's the most transparent way of doing the pre-processing in R. As you read around and look at other examples, you'll see that there are a variety of ways of doing this pre-processing. Those ways, I've taken a way that requires actually a fair bit of programming. So there are ways where you can do it even just in one line of code to get it into the right format. Now, the reason I haven't done that is that I like to go through and really sort of do some extensive pre-processing on the text before we work with it. I've found that typically helps quite a lot. But of course, with your own texts, you can experiment to see how this works best. Now, another footnote that I'd like to give you is, we're doing this using just a basic neural network and a document term matrix. In real world applications, that is to say Google Translate or predictive text in Gmail, they use much more complicated variations of neural networks. So firstly, for pre-processing, they use a stage called embedding. So we're using here very much a bag of words model, where we're just pulling words out and order doesn't matter terribly much. In embedding, it actually looks at the context of different words. So it puts them there within a particular structure that captures order and form within the language. So that's obviously a much more advanced way of doing it. Then there's a particular type of neural network called a convolutional neural network that takes better account of that embedding. Okay, that can work with the fact that there is information in the position of a particular type of data relative to other pieces of data. Now, I'm saying that both of those are outside scope here. I just want to work with the basic models. And we'll see in the demonstration that even with this pretty simple setup, we can actually do pretty well in solving our classification problem. Okay, so that's given you the material. Like I said, it's a crash course. Okay, so we're going through and doing this very quickly, and we want to get to the application. So I do encourage you to spend a lot of time with the demonstration files for this lecture. Now, the first one that I want to show you is the LPI. Remember, our problem from lecture 1 was that there's this indicator that a lot of people use. The World Bank is discontinuing it in its historical form, and it only ever had partial coverage. Wouldn't it be nice to use an easily available data set like the World Development Indicators to predict the LPI? Okay, so basically fill in the blanks from existing years, and then to be able to update it when the World Bank is no longer conducting surveys. So we've seen results using the lasso technique. Now, if memory serves, we had a root mean squared error of about 0.2. Okay, so when we're doing this sort of a problem, we always want to have a benchmark. Okay, the lasso is pretty much the simplest model that we could apply, and we get a root mean squared error of 0.2. Now, just because a neural network works well in some settings, it doesn't mean that it will necessarily work well in this one. So I'm actually presenting this as an example of how to set up a problem that you're already familiar with. Okay, so there's no barrier in understanding the nature of the problem. But of course, when you look at it, you only want to retain the model if it does a better job of predicting than some simpler model that you've already run. So it's really just about getting the hang of working with artificial neural networks. So the pre-processing is going to be exactly the same with one minor change as we've seen in lecture 1. So we can then just get straight into looking at how the modeling is different. Now, artificial neural networks probably sound pretty intimidating by this point, but of course there are packages for that in R. The main one that we're interested in is Keras, and it makes building artificial neural networks very easy. Now, Keras, the coding in this, people always say that they've got a preference for coding in a particular language. When you're using packages like this, you always end up using code from all sorts of different languages. So we're going to use an R interface to Python tools that are actually coded in C++. Okay, so we're doing something sort of fairly convoluted, but the back end is coming from a package called TensorFlow. And this is actually from the guys at Google. So Google obviously has a lot of machine learning, artificial intelligence, deep learning expertise. And this is a set of routines and tools that they've made publicly available. Okay, so it's extensively used in artificial neural network applications. Now, the easiest way to build a neural network in Keras is to go sequentially. So basically, if you've got 10 layers in your model, you just add each layer separately. Okay, so the way that we do that is by adding what are called dense layers. So those are the sort of standard types of neural network layers that we've been looking at in the motivation for this. I put the code on the left-hand side. So the first line just tells Keras that we're going to set up a sequential model. Then the second set of instructions actually sets up the model. So here we're setting up a first layer that has 55 input points, then 50 neurons in the layer with a ReLU rectified linear activation function. Then in the next layer, we've got 25 neurons, then we've got 12 neurons, and then in the output layer, we've got a single output. Okay. Now, notice that I've specified the activation function as rectified linear for all the hidden layers, and I haven't specified an activation function for the output layer. Now, if you don't specify an activation function to Keras, it's going to assume that you want a linear activation function. Okay, so this is basically a regression type neural network where we're taking a whole bunch of inputs, we're playing with them in the model, and then we're giving an output that doesn't have any particular bounds. It's not 1 or 0. It's not only above 0. It can take any numerical value. So it's a pretty typical setup for a standard quantitative prediction ANN. Oops. Okay. So then once we've got the model set up, we need to compile it by telling Keras which loss function we want to use. Here I've said MSE, which is mean squared error. We need to choose an optimizer. That's something we're not particularly interested in. You can just always use this, this Atom option. It's a good general purpose optimizer. And then we train the model by telling Keras to fit it using the training data. Now to do that, we've got to specify the number of epochs, the batch size, and the validation split. These should all be familiar from the preceding discussion, basically telling it how many times it's got to iterate, how much data it's going to use before it updates its weights each time, and then how much data it's going to use for validation. Okay, so you can see here we're using 25% of the data for validation. We're doing batches of 100 and we're doing 500 epochs. Now, what about the grid search? Okay, so in that model that I just set up, there's a whole bunch of hyperparameters that I've just assumed that we know. Of course, in reality, we don't know them. Well, TF-Runs is a great little package that helps you automate the grid search. So what I've done here in the code on the left-hand side is to set up a list for my grid search. And so what I'm doing here is searching over 10 layers for combinations of 10, 25, and 50 neurons. So it's going to do all of those combinations. And then I've said, okay, let's try dropout regularization as well. Remember, this is to avoid overfitting. We set a certain percentage of nodes equal to 0. We're going to try rates of 0, that is to say no regularization, 0.1, 10% randomly set to 0, and 20% randomly set to 0. Now, working with TF-Runs requires a little bit of coding. Okay, basically we start with an R file that contains your core neural network code. Okay, and a set of flags for each of the parameters that you're going to be doing a grid search over. So basically, you've got to tell TF-Runs which hyperparameters you want it to do the grid search over. Then in your main file, you call TF-Runs with a list like this one that defines the hyperparameter space, and then you tell it where to look for the core code to run. So here you can see I've just called it corecode.r. Then you tell it where the flags are, that is to say in this grid search list. And by using sample equals 0.01, I'm telling it to do a random grid search using only 1% of the total number of models. Okay, so as I said, the example here has got up to 10 layers in the neural network with combinations of 10, 25, and 50 nodes and different types of dropout regularization. Now, the search is random, retaining 1% of the models defined by the list. But you can see that with a model like this and the number of parameters that I'm looking over, even with only 1%, I've still got to look over nearly 2,000 models. So you can see that it starts to become very time consuming. Okay. Oops, going the wrong way. Oops, sorry. Okay, so let's now dive into the code and we can have a look at how this works in practice in R. Now, I'm not going to run the first bit of this code. So when you look at demonstration 1, that is to say the demonstration 1 file, the first half of the code should be completely familiar to you from lecture 1. The only change is this line here. So basically, just before I do the testing and training split, I scale the data by normalization. Now, this is very straightforward. I simply create a new variable called xScale, and I say that I want R to normalize that data. That is to say, transform everything to mean 0, a standard deviation of 1. Okay, so I'm not going to run this code, but once you run it yourself, you'll see that you get the data the data elements as defined up here. And what I'm interested in is the new code to set up a neural network. Now, this first bit of code, which I'll start running while I talk about it because it takes a bit of time. There we go. Okay, so this first bit of code sets up just a very simple neural network to try and get the hang of how we do this in R. So as I said in the slides, first we've got to tell Keras that we want a sequential model. Then we've got to send it the structure of the model. Okay, so in this case, we're doing a 3-layer neural network with 50 neurons, 25, 12, and then a single output. Okay, so this is, we've got a single output because we've got our one LPI number that we want to predict. So I've set the model up much as you saw on the slides. Now you can see here that it takes the computer some time to do this. Now the primary reason why it takes some time is because I've set the number of epochs at 500. Okay, now as the model runs, you see this figure being drawn on the right-hand side. Now, this one is not particularly informative. We would need to zoom in on this to really get a sense of how the model is performing. But what it shows you is this combination of training loss in blue and validation loss in green. So remember, if we were doing a real application here, we would want those two to be very, very close. Now, they look like they're exactly the same. Of course, that's because of the scale. They both start off really bad and then they get much smaller. We would need to zoom in on that graph to see how we're doing with overfitting. But you can see here that we've gotten a loss of about 0.16. Okay, so a mean squared error in this case, since that's the loss function we specified, of about 0.16. Now, the next bit of code says, okay, that's a simple application. Let's now run a grid search over some more interesting models. Now, as I said, there are two elements when we want to run a grid search. The first element that we need is in the LPI neural net core code.r file, which is also in the folders that you've got. So here is where we set up the flags, okay? Basically where we tell TF runs which are the hyperparameters that we want to run the grid search over and which other hyperparameters we're just going to set. So the ones where we're going to do a grid search are called flags, okay? And here it's very easy to set them up. We've simply got integers for the number of neurons, and then we've got a numeric for the dropout. Now, we need to be very careful to define these properly. So the list of flags has got to be exactly the same in this document, and it's got to correspond between this code and our main code. Then once we've got that, we simply set the Keras model up in exactly the same way. We say that it's a sequential model, then we add these layers using the flags, okay? So here you can see that we're saying that for the number of neurons in the first layer, please look at this first flag, dense units 1. And for the dropout rate, look at this flag, dropout. Okay, so it simply builds, if you like, a structural model where each of these flags can then take a different value. Then once we've got it, we compile the model as always, and we fit it. Now, I would advise you to fit it using a small number of epochs. Okay, here I've taken a batch size of 100 and 100 epochs. Obviously, the more epochs you add, the longer the model is going to take to run. Okay, so these things can go for days if you don't make them as small as possible. Okay, so then once we've got that, we simply define our grid search here. So you can see that I'm doing it through lists and then sets, vectors, lists within those lists. So dense units 1 through to dense units 10, okay, all corresponding to those terms that I used in the core code. And then we set up this object called runs, which is where we use the function tuning run, and it tells it to do a grid search over this list that we've just created. Okay, now I'm not going to run the code here. You guys, please do run it, get a feel for how it works, but it is a bit time consuming. Now, what it gives you when you run the code is this object runs that gives you the performance of each of the different models. So what you're then going to want to do is, and it saves them into your working directory as well. So you get a complete list of all of these models. So what you're going to want to do is then order them. Okay, so to look at the prediction accuracy or the mean squared error in this case, and then to take the model that has the minimum mean squared error. So I've gone through and done that. Your results, of course, may be a little bit different because there is a stochastic component to this. But at least when I went through and ran it, the best performing model was this one here. So I'll just run that again now. And you can see that there's no particular rhyme or reason to the number of neurons. I found that the best dropout rate was 0. Okay, so it tended to work best when we didn't set any of the weights to randomly be 0. But then we have a mix of sort of widths in each of the hidden layers, going from 10 in some of the middle layers to 50 in some of the early and late layers. So of course, if we wanted to go through and do this in more detail, we might search over a broader space. We might take a larger proportion of the models. We might search over some different hyperparameters. Maybe we would also search over the batch size. Maybe we would search over the number of epochs, these sorts of things. But I just want you to see the basic sort of results that we get here. You remember when we did the evaluation before, I think it was about 0.16. And once this model goes through, we'll run the evaluation again and we'll be able to compare to see just how much better we actually did. You can see here, it may take a little more time or a little less time on your computer, depending on what your processes look like. But when it comes out, we get a loss of about 0.13. Okay, so we've improved somewhat, okay? Obviously, in a real application, we would go through and do this in a lot more detail, but hopefully that's given you a sense of basically what the workflow looks like. Now, once we've got all of that, we can go through and calculate the root mean squared error. And, you know, this is something that's important to keep in mind. I've got it here saved as RMSE_NN, and you can see that it comes in at about 0.39. So it's actually a fair bit worse than the lasso, okay? Now, maybe if we play around with the hyperparameters, play around with the structure of the grid search and other sorts of tweaks that go into this, maybe we can do better. But at least with these simple models that we're looking at, we say, okay, this is great. We've learnt the technique. We're familiar with the workflow. We see how it works. But if we were doing this in a real application, we'd probably go back to one of the simpler models. Okay, so more complex is not always better when it comes to machine learning. Okay, now let's look at the second demonstration. So you've already seen the input and the output data. Now, this is the one where we're trying to work with text. So we've downloaded this information from trains. We've got the human coder's description of a measure, that is to say a non-tariff measure, and then we've got the masked classification of that measure. We're going to simplify the problem by looking at the letter codes only. We're not going to do the full alphanumeric code for each of these. If you want to extend the work, please feel free to do that. But we're just going to look at the letters. So basically classifying these NTMs into the right chapter based on the text. So pre-processing is going to use the tools that you're already familiar with from the previous lecture, but there are a few points of difference. So in the previous lecture, we looked at all of the words in the document. Now, just to keep the model tractable and something that can run in a reasonable amount of time, plus to get rid of some of the words that are not terribly meaningful, it's common in these kind of text applications to trim down the size of the input data. So basically to set some ceiling on the total number of words that go into the model. Now, once we've done all of the pre-processing, we need to make a little tweak. So you remember when we did the demonstration for the previous lecture, we put everything into a document term matrix for the latent Dirichlet allocation. But then when I clicked on the document term matrix, it came up with this kind of description of the object. So it is a special object class of its own. Keras can't work with it. Okay, so when the tools that we use to produce the DTM can get the data into the right format, but then we need one more tweak to get it into a format that Keras can work with. It's got to be just a simple matrix. So we need to convert it to a matrix. And then the final trick is to use this two-categorical function, which changes the factor list, that is to say the numerical codes that we're interested in for the mass classification, and it changes them into a matrix with numerical dummies, because that's the format that Keras prefers for its outputs. So it doesn't like to see a vector of kind of category 1, category 2, category 3. It likes to see a matrix where category 1 is a column and we just have a 1 or a 0, depending on how it's scored. Then category 2 is another column. We have 1s and 0s depending on how that's scored, etc., etc. So all of these are little tweaks. Some other little tweaks, we've got to specify the loss function differently. For binary classification, we typically use a function called binary cross entropy. Again, if you want to read into how it's defined, please do look at some of the other sources. For multinomial classification, which is what we're interested in here, we're going to be interested in the categorical cross entropy. Okay, so now let's look at the application. So this is in lecture 3, demonstration 2.r. Let me quickly just read in the data and get the pre-processing going. Pre-processing actually takes some time, and I do encourage you to go through and look at how similar this is to the pre-processing that we did in the previous lecture. You can see that we're tokenizing as the first step. We're then removing stop words. Now, the trick here is that I define what I call rare words. Okay, so I set a number of words as a maximum, max words, in this case, 2,000. And then simply by counting the frequency with or the number of times each word appears, we can order the list and then simply drop a number of words equal to the total vocabulary count less the number of words we want to retain. Okay, so there are a few extra steps in the code to go ahead and do that. Then making the document term matrix you're familiar with from the latent Dirichlet application, allocation, sorry. Then there's just one more step to turn it into a matrix and then into a data frame. And if I look at what we get when we do that, it's just going to take a second to come up. It's not a particularly small matrix, but you can see here that we've got exactly what we want. So each word is a column, and then each cell shows the number of times in which that word appears in a given document. So each document in this case is a description by a human coder. Okay, so once we've got that, we do our usual scaling of the data. So you'll see again here, we've got a normalization, and then we've got a testing and training split. Now remember, I'm starting here with 2,000 words in the vocabulary. Again, I'm not showing you a grid search. In this case, if you were doing this for a real application, you would indeed do a grid search over hyperparameters. But what I'm going to do first is just run a very simple model to give you a sense of both how it works and how well we can do. So I set it up as a sequential model. You'll see in this case, we've got 500 neurons in the hidden layer, then number of columns in the output matrix, which you remember is this categorical matrix that we've designed. And the number of inputs, of course, is the maximum number of words, in this case, 2,000. Now, a little trick with using text in neural networks is that the models tend to overfit very, very quickly. So the number of epochs tends to be quite small. Okay, so that's great. It makes the whole thing a little bit quicker for us. I've done it here just with 5 epochs. Now, you do some sensitivity on this if it was a real application. But you can see that when I do 5 epochs, the validation loss and the training loss are actually pretty close. So it's suggesting that we're not overfitting the data too badly. And those last few lines of code simply take the results from the neural network and put it into a data frame so that we can then calculate the percentage that we get correct. I've stored that in the object PC correct. And you can see that with this very simple, single layer neural network, we actually get about 81% right. Okay, that's pretty good. That's really strong performance for taking these small bits of text and using them to classify the NTMs that they're describing. Let's run a more complex model. And again, hopefully this is all familiar to you now. We're simply setting up a sequential model in Keras. In this case, we're starting with 2,000 words, then we're doing a descending number of neurons. I've just said 1,000, then 500, then 250, then 250, then 250. So it's a multiple layer neural network. Now you can see when we run this one, it's still only 5 epochs, but it looks like it's maybe starting to overfit a bit because we do get this significant gap between the training loss and the validation loss. But, you know, when we look at prediction accuracy, that is to say the percentage correct, we find that, again, with a very simple model, we're getting 87% right. Okay, so that to me is pretty good. So all of that to say, you know, please do spend some time with the code, step through it, make sure that you're comfortable with how it works. And in particular, I always think that the hardest part of this exercise in terms of mechanics is actually getting the data into the right format. So please do go through and step through each of the manipulations to see what we're actually producing in each of these pre-processing steps. But then, you know, the takeaway hopefully is that even a simple neural network can actually do pretty well at a prediction-based, a text prediction problem. So using text as the input, and in this case, a classification problem where we're doing a multinomial output on the end. Okay, so that brings us to the end of the lecture. I'm not going to repeat the takeaways. Again, you're going to have to spend a lot of time yourselves with this material to get comfortable with how the models work. Okay, we haven't gone through the mechanics. Obviously, we want to read up on that separately, then you should. But we're focusing here on the kind of how and applying all of this very quickly. So please do spend some time with it. Look at how the models perform. Feel free to tweak the code and see if you can do a bit better than I have in these applications. You should be able to, particularly with the LPI one. I think there's huge scope to try and improve that. Of course, other ways that you can do it. You can turn the LPI problem into a classification problem where we're looking at membership of the LPI quintiles. Okay, maybe that's going to work out a little bit better for the neural net. So all of these things you can explore. Get comfortable with the grid search and how that works. And then once you've got all of that, hopefully you've got a sense of how we can take text, use some of the processing techniques that we looked at in lecture 2, and then put it into a workflow that resembles what we started with lecture 1. That is to say, using it to predict or classify. Neural networks tend to work pretty well with text. And again, economics research in this area is very much in its infancy. Economics, we tend to like working with numbers. I think there are other disciplines that are a lot more comfortable working with words than we are. But there's huge scope to make a contribution here if you use the tools wisely. I'll wrap up with just a few resources here that you can look at during your own time. They start off with a very simple overview of deep learning to tell you sort of what it's about, how it works, where it comes from. There are, as always, a whole bunch of examples for Keras in R, which I would suggest that you go through. Then a couple of examples of how to use text. One is a tutorial in R. Now, they do the pre-processing in a different way, okay, from the way that we've done it here in class, but hopefully moving from the raw text to the version that we use in the problem is nonetheless familiar to you. Then the last one is an application, and I think it's a really fun application. It's some researchers who've taken the Federal Open Market Committee, that is to say the central bank rate setting authority in the United States, and they've tried to use the minutes of that committee to predict economic variables. Okay, so the minutes are obviously written out in text, and so they've done exactly what we've done here. They've pre-processed the text, then they've used it as the input to a machine learning algorithm that then tries to predict economic variables based on the text. Okay, so we'll leave it there, and I look forward to talking to you further about this in the live session.